So we are going to have our next lecture, which is going to be a continuation of things we were doing previously. So if you recall, with any matrix A, we had associated 4 fundamental spaces. These were the null space of A, which we generally denote by NA. Then we had the column space of A, which we will denote by CA. Then we have the row space of A, which we can denote by RA for now. And then we have the so-called left null space, or we also call it as the null space of A transpose. Now one may wonder why we are so much interested in this particular null space of A transpose. Once we proceed, we'll see there is a reason why we are so much interested in this null space. Now, let me recall something that we did last time about null spaces. We simply defined null space to be all those vectors x such that A times x is 0. Okay. I've deliberately left a few details here. When you say A is a m by n matrix, so it has m rows and n columns. Okay. So the thing is, we can view this thing as, when we say A is m by n, then this vector x must be of the size n by 1, and this vector 0 would be of the size m by 1. So in other words, we can think of A as a function from the space Rn mapping to the space Rm. Now this is not just any function. This function has some nice properties which makes it more useful for us. We checked last time that it satisfies 2 things. The A of x plus y is A of x plus A of y. The second thing it satisfies is A of alpha times x is alpha ax for any scalar alpha. Okay. These 2 properties you can check are true whenever you multiply a matrix A to a vector x. And these 2 properties are what we call as it tells you about the linearity of the function A, that the function A is linear. Now, as you shall see, we would be very interested in these functions originating from R into Rm, which have these properties of linearity, and our entire study will be focused on that. We will also see that any function which satisfies these properties from R into Rm, that means any linear function from R into Rm, can be represented by a matrix, and it is simply a matrix multiplication. So we keep on going back and forth between these concepts, and once and for all we get some ideas. So let's see what was null space, then I'll come back to all the other spaces. I'm just trying to recall some facts about null space. Okay, so we can think of null space. Another way to think about null space could be as follows. We can say, well, all those vectors in the domain that get mapped to the zero vector of the codomain. So if, let us say, my function was from, say, R2 to R, what we are saying is, what are those guys in here which get mapped to the zero vector of R? So this is R2 and this is R. So we are looking for those guys X which get mapped to the zero vector. So in some sense we are just interested in the so-called values at which the function takes the value 0. And why is this interesting? It will become clear after some time. Why are we so much hung up on just the 0 alone? But we have proven certain facts. The null space is a subspace of Rn. So we'll continue from there and try to figure other things out. But the point I want to emphasize is that instead of just viewing it as a matrix multiplication, you should start viewing it as a function from one vector space to another vector space with certain special properties called linearity. Okay. Just to make the example a little more clear about this one, suppose I was given this function A, which takes the vector xy and maps it to x plus y, x minus y. We can check that it is a linear transformation in many ways, but let me not focus on that. Let me show you something else. I can think of it as a matrix multiplication, 1, 1, 1 minus 1, x, y. So basically this function can be thought of as a matrix multiplication, and we want to figure out what is the null space of this. This function which is from R2 to R2. That means what are those guys which will map from the so-called zero vector to what are those vectors which will map to the zero vector? Okay. So one way of thinking of it is as follows. I can try to find out x and y which maps to 0. Let's try to do that, which is basically that we are trying to solve this homogeneous system of equations. So finding a null space is basically solving a homogeneous system. Of course we can solve this, we have a bunch of ways of knowing it. But before we even solve it, I want us to recall a few things about the homogeneous system. Any homogeneous system, it is guaranteed that it will have at least one solution, namely the trivial solution. So, since the homogeneous systems always have zero solution. What does this mean for us? It means that a null space will always contain something. Okay, so the null space will always contain the zero vector. So what it is trying to tell us is, no matter what function we are dealing with, any linear transformation, the zero vector is definitely something that would map to the zero vector. Question is, are there other things which can map to the zero vector? If yes, what are those? We want a complete description of them. If not, then does this make our function a bit special, that only the zero vector can map to the zero vector and nothing else? One obvious thing which jumps out of this picture is, suppose there was another vector which could map to the zero vector, then at least we have two things which are mapping to the same thing. That means the function cannot be one-to-one. So that means somehow null space can tell us whether our function, whether our linear transformation would be one-to-one or not. Okay. Okay. So let's try to solve this guy first, our example that we are dealing with, and see how it gives us the answer. So let us say we solve this system of homogeneous equation. We go to our old method of doing things, which is Gaussian elimination. So if I do the row reduction, I will get 1, 1, 0, minus 2. So what I'm doing is basically row 1 added to row 2. Minus rho 1 added to rho 2. And this is what we get. As you can see, this is in echelon form. So what we get is that x plus y is 0 and minus 2y is 0. This means that x is 0 and y is 0 is the only solution. Since this is the only solution, that means there's nothing else which is getting mapped to 0. So possibly the function could be one-to-one. See, right now we can't guarantee that no other vector cannot map to some other vector. All we are saying is, with zero vector is the only vector which maps to zero vector. Does that guarantee me one-to-oneness? Maybe, who knows. But right now we don't have sufficient information, so we'll have to figure things out. But one thing I should remark upon is, if you recall, having only the zero solution for a square matrix told us something about the matrix. If the homogeneous system has only the zero solution, then we knew that the matrix must be invertible. So the matrix is invertible. Could it be that somehow null space has ties to the invertibility of a matrix? Or can null space help us determine if the matrix is invertible or not? So these are the questions we should ask ourselves at this point of time. How is null space going to tell me things about matrix that we are dealing with? Okay. So these are some questions we want to seek answers for. So does the null space one-to-one mapping? Does it say anything about invertibility? If yes, how and why? So let's try to do one thing at a time. What is the connection between one-to-oneness and null space? So let's start with a linear transformation from Rn to Rm. So suppose this is a linear transformation that is 1 to 1. Then null space of A, which we call as null space n of A, can only have the 0 vector. Now this is an obvious consequence because if the function is 1 to 1, we already know 0 maps to 0. So there is nothing else that will map to 0. So saying the null space will have only the 0 vector, it's a trivial consequence of 1 to 1ness. What we are interested in is the so-called other part, or the other direction. If the null space of my linear transformation has only the 0 vector, then A is a 1 to 1 transformation. This is the one that is of more interest to us. So let's try to see if we can have a quick proof of it. If this is true, then that means null space having only the 0 vector guarantees me 1 to 1ness of the transformation, and 1 to 1ness of the transformation may help us discuss about invertibility if n and m are the same thing. Okay, so let us start with the basic definition of 1 to 1ness. What if AX1 is equal to AX2? By the linearity, at least, okay, can we write it like this? Now by the linearity, can we say this is the same as x1 minus x2 getting mapped to the 0 vector? This is due to linearity. Okay, so we are back to sort of a homogeneous system, and then we use our information null space as only the 0 vector. And here you are saying this vector gets mapped to the 0 vector. So the only possibility could be that this vector itself is a 0 vector. This tells us that the vector x1 and x2 must be the same. This tells us that A must be 1 to 1. Notice, I'm not saying anything about invertibility yet. The reason being, we are working from Rn to Rm, and n and m might be different. So 1 to 1ness doesn't guarantee me invertibility because the matrix might not be even square. However, if it was a square, then yes, we have a guarantee that it would be invertible also. So let's take a special note of it. Then null space being just a 0 vector, guarantees me the invertibility of A. Okay. So at least we have answered the questions that we had posed for ourselves. How is null space connected to invertibility, and 1 to 1 is. Now comes the second question. What is the column space of my matrix A? And can I view column space also as something to do with the function? So let's try to answer that. So I'll give you two ways of looking at the column space. One is just looking at a matrix, and then we will think of it as something to do with the function A. Okay. So I'll give you the first definition of the column space. This is the definition which most people understand fairly well. However, I would recommend you to start thinking more about the other definition that I will give you, because that is a more useful way of viewing things rather than this one, even though this is very easy to understand. So what is the definition of a column space? Column space of A is the space, well, the space made up with the columns of A. So in technical terms, it is the space. When I say made up, the technical word I mean is this: the space is spanned by columns of A. So as I said, it's a very easy thing to understand. Okay. So let's first focus on this definition before we move a little bit. Suppose somebody gave you this matrix A. Let's say 1, 1, 1, 2, 2, 2, something like this. It's a 3 by 2 matrix. I want to know what is the column space of A. So I want to know what kind of things can be spanned by these columns of the matrix A. So crudely speaking, what will I do? I take this first column 1, 1, 1. I'll say, okay, I'm going to multiply it by some x, and I take 2, 2, 2, and I'm going to multiply by y, and I want to know what are all the possible things I can produce by choosing various x and y's. So think of it as two ingredients have been given to you and you are trying to cook something out of those two ingredients. So you're trying to find all possible linear combinations or all things that you can make up out of those two ingredients. Now, for example, right now this is a big simple description. A question can be asked: will this vector, say 1, 0, 0, belong to the column space of A? So here's my column space. Does it belong to this column space? That means, can I produce that vector as a linear combination of these two vectors? So how will we proceed? Well, we want to know, does there exist x and y, some real numbers, for which I can take this guy, take this vector and produce this vector. So eventually, what are we doing? Aren't we back to solving a system of linear equations? And if you recall, when we were talking about the consistency of a system, this is what I had mentioned. That this system can be thought of as a system of the form AX is equal to B. So what are we asking? We are just asking, what are those right-hand sides for which the system is consistent? So if you think of this column space business, it's nothing new. It's just that we have given it a sort of different picture, and we are asking the same old question. What things are valid right-hand sides? So we can rephrase this as follows. We can say B belongs to the column space of A if and only if AX is equal to B is a consistent system. So as I said, I'm not going to solve it because we already know how to solve system of equations and check their consistency. However, for the sake of understanding, let us try to see, is this system consistent or not? Well, let's see. Is this system consistent? Will 1, 0, 0 live in there? Okay, so let's waste some time on this one. Here is your 1, 1, 1, 2, 2, 2. Remember our augmented matrix? And we want to figure out what will happen. So I'll do some row operations. So what I'll do is I'll take -1 times row 1 added to row 2, and same thing for row 3, and this is what I get. As you can see that we have a problem here and the system is inconsistent. Because we have a pivot entry in the right hand side column. Remember, pivot entry in the right hand side column basically told us that the system will be inconsistent. Or if you want, you can write them as equation form and you will get 0 is equal to -1. Hence it is inconsistent. So what does this mean? It means 1, 0, 0 does not live in the column space of A. So the next question would be, okay, 1, 0, 0 doesn't live, what else lives? What kind of things can we say live in that system? To answer that, you will see we are going to do the exact same thing that we have done before about consistency. Okay. So the next question we are asking is, what vectors P belong to the column space of A? So, based on the remark I made, I just want to find what right-hand sides will make this system consistent. So again, using your row reduction techniques, you can say this is 1, 2, 0, 0, 0, 0. B1, B2 minus B1, B3 minus B1. Okay. We can do a further row reduction, or let's play it a different way. So this is what we get. So for consistency, there are two things that we need. One of them is B2 should be equal to B1. The other is B3 should be equal to B1. In other words, for consistency, we are saying B1 must be equal to B2 must be equal to B3. That means all the three components of the vector should be the same, and then this thing will belong to this column space. So how do we describe the column space? We will say that the column space of A consists of all the vectors B1, B2, B3 such that B1 is B2 is equal to B3. So this is what we get just simply out of the definition of the column space. But the interesting part still remains, how should I view this as in terms of the function represented by matrix A? So I'll make a quick remark about that, and then we'll continue it later on. How should I interpret column space of A? So let me bring back the function idea. You have a linear transformation from Rn to Rm. Now, from now on, I will not say it is a linear transformation because all the functions that we will be dealing with will actually be linear transformations. So unless and until there is a reason, I will just assume linearity is always there. Okay. Column space of A. If you recall the way we described it, was all those right-hand sides for which this matrix equation had a solution. So let me recall, we said AX is equal to B. So B belongs to column space of A if and only if this is a consistent system. Okay. Now, how will I interpret over here? Think of your A as a function which is acting on the vector x, and then it is giving me a vector b. So we are saying whenever this thing has a solution, all those b's which I can capture in this way would be in the column space. So can I say another description of column space would be all those vectors b in Rm. Notice in which space they are. They are living over Rm, such that Ax is equal to b is consistent. Okay. In other words, isn't this what we call as the range of the function A? So column space is nothing else but simply the range of this linear function. What are the things which we can hit in Rm based on the inputs we have in Rm? So null space was special vectors in here which map to the 0 vector, and column space are all the vectors in the codomain which can be mapped using vectors in the domain. In other words, column space gives you the range of this function. Now, there is something that comes out of this example fairly easily. However, it may be something that you may not notice immediately. Question is, what is the connection between the range and the null space? Which the null space of A are related. The answer turns out to be one of the most fundamental theorems of linear algebra, which we will see later. It's called the rank nullity theorem. It connects all these things and gives you a way to learn about each other. And we shall see, that would be our next aim. After we are done with all the fundamental spaces, we will see how they are all related to each other.